So today, as Amber mentioned, I'm going to be presenting on the work I did for my master's, and it was a kind of a collective effort with some of postdocs at U of T about a toolkit for really assessing some of us bridging strategies when there is an unplanned rail disruption occurring. So there are going to be a bit of a background objective. I will go very briefly over our methodology, and the focus will be on our use cases, which is basically one on assessment scenarios of bus bridging and shuttle bus deployment. The other one will be focusing on optimization. So from data we obtained by TTC on unplanned rail disruptions, we noticed that around 144 unplanned subway closures occurred. And for those closures, up to 6,500 shuttle buses were used to serve passengers instead of the closed rail service. And we also noticed that up to 70% of these buses were actually taken from existing operational routes, which means that they're not only impacting the system, the subway system, but also the bus network. We also found that the economic cost of major subway passengers in a large city like New York was estimated to be around $389 million annually. And this brings us to the need actually to have such tools that can help agencies in deploying shuttle buses in a better way and improve their service to be more efficient, as some of the actual methods are kind of simplistic, and this can lead to really, as we saw, extensive delays and degrade the quality of service. So our basic main objective is to provide a tool, as I mentioned, to help agencies evaluate different shuttle bus scenarios. And we really need them to have some measures that to help them assess these scenarios based on bus passengers and train passenger delays, in addition to some measures that can really help them assess the shuttle buses. Are these shuttle buses being used efficient or not? And this is a very simple schematic on the overview of the methodology. We actually did a macro simulation model based on deterministic queuing analysis. We basically model our disruption as we see in the figure here. Trains can actually continue their service due to some unplanned closure, as we can see here in red, and they turn back, dropping all their passengers at these two end stations. So different buses from different routes in the system are usually requested. They travel all the way from wherever they are, and then they start serving as shuttle to bridge the disrupted segment and serving passengers. So our method, the macro simulation that we did, tracks these buses from the moment they leave the service until they arrive to the disruption segment, and then they start serving passengers. And I would, again, we use deterministic queuing analysis to actually estimate the wait time and the travel times for these passengers being served by the buses instead of the rail. And at the end of the incident, when buses go back, we also kind of estimate the time that's needed for the queues to dissipate, as the capacity of buses is much smaller than the capacity of rails, and there's queue buildup. So to begin with the use cases, I will start with our Dash Bus Planner, which is a tool that helps in assessing different bus bridging scenarios. So this tool takes into consideration two different inputs. The first input is related to the incident itself, and it is a user-specified input, which means the transit agency would input what's the incident location, the expected duration of the incident, and whatnot. And most importantly is what's their shuttle bus plan, which means how many buses they need to request for a certain incident, where are these buses coming from, which route, and whatnot. And then in order to evaluate some of the metrics, user delays, we need to have some data inputs that are related to the transit network characteristics, the train and buses travel times, and train buses ridership. And then a Dash Plus planner actually evaluates a bunch of metrics related to the passenger delays, related to shuttle bus performance measures, their efficiency, the detailed measures at each disrupted station, and a lot of other metrics. So we use this tool in one of the real case study. It's an actual incident that happened in the morning peak period between Bloor-Yonge and Eglinton, which is basically Midtown Toronto, and closing 6 stations for around 30 minutes. And the results that we got, the numbers in red, they present the passenger delays, the total passenger delays in hours due to this incident. And if we look at the bus metrics, we can see that of the 23 requested buses to serve this incident, only 15 buses made it to the incident and they were able to serve, while 8 buses were kind of a waste of time where they traveled all the way from their depots, but they could not, from their terminals, but they could not make it to the incident, and then they had to turn back, and this is kind of a lost scenario. So through this tool, we can actually know the exact bus routes, the bus routes that made it to the incident and the bus routes that did not make it to the incident on time. And then what we did, we said, what if we eliminate these buses that didn't make it to the incident? And our analysis showed that we actually was able to reduce the bus users' delay by 50%. And then we have no waste. But what if the incident requires more buses and requires actually 23 buses to be there and serve as shuttle? So we tried to create a scenario where we select these buses from closer routes. So you can see here in the figure that we selected the ones highlighted in different colors are the routes that are being selected, and the red, dark red is the incident. And we kind of tried to just kind of randomly selecting these close by routes. And we actually saw like a major change in the shuttle bus performance metrics, where we had the deadhead time, which is the time spent just going from their service to the disrupted station, decreased significantly, and this increased the on-shuttle service time. And this was reflected by a major reduction in subway riders' delay and a very slight increase in bus riders' delay. And this could be attributed to the maybe higher ridership for these routes and other factors. And here comes the need to actually have some sort of an optimization to know what's the best plan. And our optimization basically is based what we need to get instead of us giving the tool the assignment of shuttle buses. We need to have this as our output of the model, which basically give us the optimal number of shuttle buses, what are the optimal bus routes to select these buses from, how many buses from each of the routes, and to which end station the bus should start serving. And all these depend on different factors that we took into consideration. We used evaluationary algorithm. I'm not going to go into details, but our focus was to minimize the total users' delays, which basically bus riders' delays and subway passenger delays. If we look at our comparison between the actual plan versus the optimal plan for the incident, we can see that the average deadhead time reduced significantly to around 2 minutes. Before it was around above 16 minutes. This is reflected also by the on-shuttle service time. We can see on these pie graphs on the left, on the right, that in the current plan, more than 50% of the time was being wasted on the roads and not in service, not in shuttle service. While the optimal plan showed that actually 90% now of the time of these shuttle buses are being spent on shuttle. And this kind of gives us the importance that optimization is needed to kind of have a better plan. We did some initial visualization with Trapeze, our partner for this project, and it is a user-friendly dashboard that agencies can select their incident, the time of the incident, which and stations are closed, and they can actually here on the figure on the left, the top figure on the left, they can drag and drop which bus routes they need to select. And then that when we run this, something on the backend runs and the model on the backend runs, and it can give us the results. We can see the results on a map view, as we can see here in the figure on the right, or we can see it in a tabulated form, and we can extract it also to Excel. The dashboard also, this dashboard is for the planning tool, but also there's a dashboard, similar dashboard for the optimization tool. So just to wrap up, what are the potential use cases of such tool? Maybe not only for managing shuttle buses and unplanned disruptions, but a key challenge that's now facing transit agencies is to really improve the management flows and overcrowding in subway systems. And what if shuttle buses can help us reduce these overcrowding? With the physical distancing being imposed and whatnot, the capacities of transit vehicles is reduced. We need also take into consideration, and when we manage rail disruptions after COVID or during COVID, and now shuttle buses are packed usually before, but during COVID, shuttle buses can't be packed anymore for social distancing, and the capacity is reduced to 810. So we can use this tool also to assess whether bus bridging is good or not, or what if we need to do like further measures to manage unplanned rail disruption. We have a list of publications that you can look at in details about analysis, about the optimization, about the planning tool itself, and the macro simulation, the modeling and whatnot. And then we would need to thank like our partners that helped us like go through this project. And if you have any questions, I'm happy to answer them now or in the chat. Thank you.